Homework 15, sampling distributions in the central limit theorem, video 3. Probabilities involving the central limit theorem. For example, let's say in a population we know that the average is 50, and we know that the standard deviation is 5. And we pick a sample of size 64. So wrap your mind around that. We got a population of values that could represent anything. Let's say they represent ages. And we know that the average age in some sort of population is 50, and the standard deviation of those ages is 5. And we go and pick 64 people out of this population. What is the probability that the sample's mean is less than 49? In other words, what's the probability that if we pick 64 of these people, their average age is going to be less than 49? Well, first off, let's figure out what probability question this has been asking by drawing a picture. Since we'll draw the picture in a second. First, let's figure out the problem we're being asked. It's a probability, so we're going to start with a capital P. And something is less than 49. But what? It is crucial from this point forward that when you set up a probability problem, you put the correct variable here. And the correct variable is the variable that represents this, the sample's mean. And the variable for sample mean is x bar. So this is the question we're attempting to answer. Now, before we draw the bell curve for this, we should make sure that it's actually a bell curve. In other words, we need something that provides evidence that our x bars are normally distributed. And remember, the central limit theorem says there's two things to look for. Number one, the original population is normally distributed. Makes no mention of that. But the other one was about the sample size. And the sample size is greater than 30. So really, I should have started this by saying, since the sample size n is greater than 30, the x bars are approximately normal. And I can say more. I can say the mean of all the x bars, the use of x bar, is equal to the mean of the original population, which was 50. And I can also calculate what the standard deviation of all the x bars is. It's just the standard deviation of the population divided by the square root of the sample size. I meant to write the numbers. The standard deviation of the population was 5, divided by the square root of the sample size. The sample size is 64. I chose 64 because it's nice to square root, and dividing by 8 is never catastrophic. 5 divided by 8 is a decimal, is 0.65. So here's what I know about the x bars. Their bell curve, thank you central limit theorem, and large enough sample size. The mean of all the x bars is 50, which means I can drop 50 in the middle. And although I'm not going to represent it on the number line, I'm going to mention up here that the standard deviation of the x bars is 0.65. And now let's go back to the probability question that we're attempting to answer. What is the probability that the sample mean, x bar, is less than 49? Well, there's a picture associated with this. 50 is in the middle, 49 is a little bit to the left. To calculate the probability that something is less than a number means that you want to calculate the area to the left. So the probability that we're looking for, the probability that the sample mean is less than 49 is equal to this left area. So all we got to do is find the value of that left area and we're okay. This is starting to look like a z-table problem. There's a catch though. This isn't a z picture. How do you know it's not a z picture? Well, first off, it doesn't say z, but even if it didn't, it could still never be. Because the z picture always has what number in the middle? 0. So if we can convert this to a z problem, we're good. Wait a minute, didn't we convert things to z's before? Didn't we have a formula previously that looked like this? This isn't the one we're going to use, because this isn't the variable we're looking at. We're looking at this variable. So what's the conversion formula that will convert an x bar to a z? Again, in the previous videos, this was the formula for converting a single value to a z. We're converting a sample mean to a z. So how do you make this the conversion formula for an x bar problem? The answer is you go to the right side and trick out everything x bar style. This x becomes an x bar, this mu gets subscripted with an x bar, and this sigma gets subscripted with an x bar. So it's the exact same conversion formula in the context of x bars, the sampling distribution. Again, in case you missed it, this was the formula that converted a single value x to a z. The formula that converts an x bar value to a z. You get an x bar, you get an x bar, you get an x bar. So this is our conversion formula. So once we know these values and the x bar that we're looking around, we can calculate the z. One quick comment though, if you look in the book for this formula, I'll tell you where it is. I thought I would tell you where it is. Wait a minute. Wait, are you really just going to walk up in the middle of an example and say, oh, by the way, here's the conversion formula? Oh my gosh, I love this statistics book, a lot of the things that it has, but this is the first thing that's just making my jaw figuratively drop. That there is not a formula that explicitly says this. They just sneak it in an example out of nowhere like, well, duh, but how silly. All right, so this is the formula for converting x bar to z. When you're doing a probability involving an x bar, probability involving a sample mean. What I was going to say is, in the book for this formula, and they do actually write it this way, normally what they do is they don't put the x bar here. Now why don't they do that? Well, because mu sub x bar is equal to mu, and it's kind of redundant. But I like leaving the x bar on there because it's a reminder that the original formula for converting x to z just gets tricked out by giving everybody an x bar in the correct place. So we can do that probability problem by changing it to a z probability problem. So now we're ready to answer this. Since we're, sorry, I don't mean to write the word since there. We're comparing x bar to 49, so this is the value we need to convert. So x bar equals 49 converts to z equals our x bar value minus the mean of all the x bar values, 50, divided by the standard deviation of all the x bar values, 0.625. And I believe this is going to be negative 1.6. But now's not the time to impress anybody. And on the top is negative 1. Who am I kidding? I know it's 1.6. All right. Therefore, I can't remember if I've introduced you guys to the 3-dot triangle. If we get through hypothesis testing, and we'll at least take a brief look into it later, it's a symbol that will show up visually there, but it's basically a symbol that says, I'm about to answer a question, or I'm about to draw a conclusion. Therefore, the probability that x bar is less than 49, which is the question I'm attempting to answer, is the same as the probability that z is less than negative 1.6. And now it becomes a z-table problem. I'll pull out a z-table in a moment for my own references, but just a reminder of how the z-table works. The left column represents the 2 digits to either side of the decimal place. So negative 1.6 is what you would look for in the left column. The top top row represents the second decimal place. So you would go to 0.0, look in the negative 1.6 row, and the number you look up is the area to the left of that z value. So if you don't know what I'm talking about, then you haven't done 7.1, 7.2. In one of those videos I mentioned that if you don't know how to use the z-table, you can't move forward. So if you're not sure what I'm talking about, go back and watch the videos for 7.1 and 7.2. So using the z-distribution table, which is in an announcement in Canvas, the area to the left of z equals negative 1.6 is 0.0548. 0.0548. So what does this mean? This means there is a, let's turn it to a percent, 5.48% chance the sample's mean is less than 49. So again, I want to answer this in the context of that I made up a moment ago, where I said, let's say we got a population of people, and their average age is 50, and their standard deviation of all their ages is 5, because somebody did the math. Then somebody goes and picks 64 people, and wonders, well, I wonder what's the probability that their average age is less than 49. The answer is 5.48%. There's a very small chance. In fact, it's almost unlikely. Remember, unlikely means less than 5%. It's almost unlikely that if I pick 64 of these people, 64 of these people whose average age is 50 and their standard deviation is 5, there's hardly a 5% chance that the average age of that sample will be less than 49. We'll take a look at another example of the central limit theorem, but most of these probability questions are really the same. Identify that it's an X-bar problem, you can usually tell because it talks about a sample and its mean. Set up the problem, convert it to a Z problem, and then get busy with the Z table. We'll take a look at another example in terms of roller coasters. That sounds fun.